I've been muted the entire time. Hi, chat. Can you change the screen so that it just shows the screen full screen? Okay. Hi, everyone. Can I see someone in chat? If anyone's here with us online, can someone just confirm that you can hear me and maybe the rest of the room? If not, I'm just going to keep going and we'll have just a quiet video, I suppose. Yeah? Okay, cool. Sounds good. Yeah, I got it. Thank you, Tyler. Thank you. Thank you. Okay, first things first, we got to get through some administrative stuff. Scan QR code to do attendance. I've already done that because I set this all up. This is just for our club. We're a student club, so we have to prove to the SU that we're a student club treating students. And then once you do voting once you do attendance, that's the word. Doing half of them doing half of all attendance sheets will allow you to vote in our annual general meeting, which is going to be at the end of the year. And then this also helps us a little bit with sponsorships, which usually just goes straight to the CTF that we'll be having. So I'll give a couple moments for that. I can copy a link into chat, which I forgot to. Ooh, can I steal it from the slides? No. Okay. Sweet. Thanks, Greg. Yeah, we'll have a link to the attendance posted into chat. I have everything else ready. Anyways, for today, we're going to look over what is reverse engineering as a general topic. And then we're just going to quickly do a web-based reverse engineering challenge, maybe to the detriment of one Manticore. And then we're going to go into assembly. So I'm going to talk about, I'm not going to go into the nitty gritty of assembly necessarily. I'm just going to be here to talk about how you can reverse engineer a binary challenge that you would usually see in a CTF. And then we're going to go through some tools that I personally like to use and I highly recommend that you use, and then close things off. Cool. So first things first, what even is reverse engineering, right? It has engineering. It sounds fancy. I'm an engineer. I'm not smart. So it could be literally anything, right? Let's say Merriam-Webster defines it as to disassemble and examine or analyze in detail a product or device to discover the concepts involved in the manufacture process, usually to produce something similar. That's my best. I really like that definition, but a wording has something similar. Wikipedia, which no one should use, has something similar. And then if you're into law for whatever reason, they also have a definition on the Legal Information Institute. However, at the end of the day, reverse engineering is the process of analyzing a solution to better understand it, or in sometimes our case, to break it. And that's what we're here for. So I'm going to make an abstraction first. It's what I like to do. I know not everyone likes abstractions. It's a very mathematical thing to do. However, we can always consider an application as a black box. So effectively, we have things going in, things coming out. Within this black box, something is happening. If we then go to analyze this black box, we'll see, okay, there's additional inner processes that are happening. In this case, we have the input. It goes into inner process 1, does something, and then it can either go to inner process 2 or inner process 3, which then gets feed out as the output. But then if we can go even deeper into each of these inner processes, and then we can continue to break down like these components and you would technically stop at a fundamental level. And that fundamental level is like technically defined by yourself. Most people would probably see it as a single line of code. Let's say like a plus equals 2 is a pretty fundamental level. If you want to go even deeper, you can always look at the assembly or machine code, which we'll get into in a bit if you don't know what that is. But you can even go into the hardware level and talk about like logic gates, transistors, electron flow. And then if you want to go even deeper to where I consider is the fundamental, we can go into logical philosophy. And that's philosophy 279 if you're in UFC, and it's a whole nother topic that I'm not going to get into. So let's access today's files. So if you saw our Discord announcement, I realize I can't post this into chat. That's hilarious with my current setup. If you go to our, if you're in our Discord, excuse me, if you saw my Discord announcement, I did send a link with a zip file to for today's challenges and also for today's demos, just so you, if you want, you can follow along. And then the zip folder is password protected, and that password is caw, cac, caw. Very Big Pie themed. Don't worry about it. I'm just going to give you some time to unzip it. You should just be able to do unzip and then intro to re.zip, and it'll ask you to type in the password, yada, yada, yada. First things first, we're going to take a look at a web challenge. This web challenge is File Vault. It's also hosted at this page. I wonder if I can paste it. I cannot. Oh, let me see if I can make this bigger. Sorry, I cannot. Hilarious. Oh, Craver, how do I highlight your comment? Oh, it's, yeah, can you show Craver 2000's comment? That's a very good point, Craver. That is definitely quite low, but if you're going to go to like fundamental physics, I would argue that quarks are then maybe spin. I don't know. Anyways, good vibes. I agree with you though. Okay, so coming back, we're talking about a web server. This web server is called File Vault, and I'm calling it a secure file hosting website, which asks you, the user, for a password before reading a given file. Again, the source is within the zip file that I gave you in the /webdemo/index.js. And then if you ever want to interact with it, it's live right now at the shown IP address. So if, let's suppose you want to read my secret, I don't know why you would. I prefer to have some privacy, but if you were to just open it right now, you will see some JSON that says, oh, there's an error, and this error is that you can't read my file. You don't know my password. And if you're wondering what this format is, this is just a screenshot taken on Firefox. It's just the case that my brain just farted. Fun. Oh yeah, Firefox formats this JSON so that it's prettier to read. But at the end of the day, it's just plain text JSON. Cool. So I'm actually going to hop over to my iPad really quick, as long as I can get the file up. Give me a second. And assuming you're reading the source code, this is, I should have the exact same source code in front of you. So effectively, at the current moment, there's quite a lot going on. I'm not going to lie. We have these are function declarations in JavaScript. So it's just a funky way of doing it if you've never seen it. Just know that this is the name of the function, and then these are going to be the parameters or the arguments of your function. So we're scrolling through. We have this very funky function called readSecret, which is interesting, but it's not being executed yet. let's figure out what's happening first at a fundamental level. So going to straight to the bottom, we're going to see what's being executed. And what's being executed is, first at least, is that using like an HTTP, we're creating a server, we're passing in this variable on request, and we're listening on a given port effectively. And then we're doing some logging, but that's whatever, we don't have access to that. Well, you guys are connected by HTTP at the moment. So that means we're definitely running a web server. Let's see what, I will tell you now that on request is another function. In fact, I have it up here. And we're taking in a request, and we're also passing through a response. But I'll tell you now that the request is something that you would create, and that would be your input. So this is your request. Pardon my pretty not great handwriting. We're making a request. It's then going into our web server, and then it's being spat out by the response. This response is what's going to come back to us saying, oh yeah, this is the file, this is what we wanted at the end of the day. So we want to create the response. And yeah, so we can see, even if you don't really know what a switch statement is, that's perfectly okay. Just know that each of these, it's checking the URL.pathname, or what the URL is asking. For example, if I look at example.com/index.html, this index.html is our path name, just if you were unaware. So we have currently two matches. We have a file.html and then API/v0/files, which that calls the list function, or excuse me, list files function, which maybe we can look into that. But recall that we pointed out this read secret. This read secret looks to read in some search parameters, namely file and pass, and then it's going to write into the response that we're outputting. So if you're wondering what search parameters are, anything after a question mark is going to be a search parameter in the form of key equals value. So let's say I want to say, let's go very computer sciencey and say foo equals bar. That means we then have a key of foo and then a value of bar. But all of this is our search parameter. Anyways, let's go into see what read secret does. Read secret we saw earlier, that's up here, perfect. So again, we're passing in the file name, password, which is file and pass, and then this is our output. Wow, that's a terrible U. Output, there we are. We're doing some fancy stuff here, but let's try to figure out like what's leading to our access denied first. Just focus in on what we need to bypass right now. So if we try to look for the string that we're getting back from the server, we find it right here. Access is if prohibited. I meant to change that. That's fun. Anyways, access if prohibited. The password is incorrect. Excuse me, I'm just gonna try to check it on chat. Okay, access if prohibited, password is incorrect. It's gonna send it back as a 403, it looks like, which is HTTP code, if you're curious. And that's caused by this line, this comparison here. File pass is not equal to password. Well, then, if we had the case where the file pass was the password, right? Which means we have the right password. What happens? Let's go past here into this read file. Seems to read the file that we want and then respond with it, unless there's something wrong with reading the file on the computer. but that's not likely to happen, so we can probably just ignore that. So at the end of the day, this is the file we want. Okay, cool. So that means we should find a way to make sure that our file path is our password. Um, and namely, we can look at the declaration definition of file paths just above it. And it looks a little funky, right? We have new buffer.from file name .toString, like lots of fun stuff. But at the end, but we might recognize one word, maybe from one cryptography workshop, base64. It is an encoding if you aren't familiar with it. So basically, you're able to take in text and then spit it out as basically shorter text. It's a way to represent information in a smaller package, typically. But it's just an encoding, and because because the file path is being created by taking in the file name, which we know, and parsing it into the string, like into a base64 string, maybe we can try to do that for ourselves. So I'm going to switch back to our slides and just kind of quickly go over what we've done so far. At the current moment, we kind of broke things down and ignored code that we don't really need to look at. This is just surrounding code that is just doing surrounding things, namely setting up the file, like setting up the file path so it traverses the right files. It sets up something called a MIME type if you're familiar with like HTTP web server stuff. Again, we ignored the like reading error because that's not something that we can control. And ultimately, we are focusing down on these two lines, 4 lines in my slides, I suppose, where we have the file path being defined from a buffer from the file name, which is being created into a base64 string. Cool. So how can we actually do this, right? Like, well, we can always use something called we can always use a base64 encoder, which basically takes in our input string and spits it out. I didn't prepare your base64 encoder beforehand, but I always like the website ASCII to hex. That's ASCII-TO hex. I know I'm swearing right now. Okay, sorry, just gotta switch over my screen so that it mirrors. I'm gonna be doing that a number of times today. Okay, so once again, I need to go to this webpage myself, forgetting. Here we are. Okay, so once again, I meant to go to, sorry about that, everyone. Oh, is the page not up? I started it. Sorry, it doesn't work. Oh, sorry about that. Give me the quickest of 30 seconds. I thought I started it, but apparently I did not. So just give me a quick moment to do so. Sorry for everyone in chat. You're going to hear my keyboard kind of go a little wild because my microphone's coming through my laptop. So let's see, Docker, compose, up, build, D. Please don't do any Docker escapes. I'm hoping this works. Okay. Now try again. Sorry about that, everyone. I just had to, I don't know, something happened, but cool. Love to hear it. So once again, we are at this page, and then if we click it, we don't have the password, and then we have access if prohibited with my typo. Cool. So now we know that the file name, recall that the file name is, I need to go to my slides, wherever they are. The file name, come on, is being parsed into base64 here. So we can go to my favorite website, ASCII2hex.com. You can use any base64 encoder. And then we can convert from ASCII into base64, which is here. And then slap that right into our website. Click on mysecret.txt, and we see my secret, that pineapple should be on pizza. And if I switch back to the page, hoping that everything looks correct. Oh boy, that is, oh, I'm not showing the right screen. Yes, pineapple should be on pizza. It's actually really good. Like, don't at me. It's actually tasty. Like, if you don't like it, you just don't have a refined taste. Anyways. You don't like it, you're wrong. Yeah, exactly. Thank you, Greg. Anyways, there is a second challenge hosted. It's at the same IP, but at port 13267. It has a very similar website that we've just went through. However, this time there's going to be a flag to get. So I'm going to give you guys 5 minutes, assuming I can set up a timer in that time. And then, yeah, I'll talk to you guys in a little bit. Oh, yeah, Bonnie? Yeah, I completely agree. Like, come on. Pineapple on pizza is absolutely amazing. Anyways, I'm going to give you 5 minutes starting now. We just have about over a minute and a half remaining, within like 4 or 5 minutes, that is. I just want to see if anyone in chat or anyone in person has gotten the flag or wants more time. I'm always going to take silence as nothing. So, but chat is always delayed. So, yeah. Do you want to check in? That is 5 minutes. Does anyone want more time? Okay, Ramesh wants more time. Do you guys want more time? Okay, I'm gonna give another 5 minutes. Starting now. Okay. Sorry? Oh, I was not added to stream. Hello, hello, hello. Hi, chat. Sorry, I had to redo some StreamYard stuff. I'm going over the solution now. So yeah, I actually have to figure out where my QuickTime player is. Okay, so once again, this page is very similar to the demo that we just went through, but it has a very certain twist to it. First of all, the biggest twist is that we want our flag.txt, but again, access if prohibited, because I just copy and pasted this. So because we don't have a password, but if I try to do the ASCII to text again, instead of my secret, we're doing flag.txt, using base 64, slapping that boy in there. Let's see. Yeah, access is still if prohibited. So, oh, there's a question in the chat. This is not all going to be about JavaScript? No. We're just getting into reverse engineering with a little bit of JavaScript to start off with. So I apologize for anyone who's like super strong binary nerd. We'll go into assembly in a little bit. We're actually just about to after this challenge. Okay, so this password does not work. Sad. However, let's try to read the source code once again. So right now, once again, we're doing an HTTP server. It has the same on request shenanigans. It has the same read secret function call. So let's jump straight to read secret, the juice of everything so far. Once again, we come across this file pass not equal password comparison, namely because our inputs are file name, password, and response. This is our output, and these two are our input. Okay, so we're comparing file pass with password. If that's not equal, then access if prohibited. And then if we do have that, if this check fails, so file pass is the password, then we go through, read the file, and then spit it back. However, this time, the file pass definition is quite different. We're looking at file pass equals quotation, this for loop, which is always funky fresh, a character code, lots of like fancy JavaScript things, this comparison here, and then some weird string concatenation from what it looks like at the bottom here. So what on earth is going on? Let's try to actually understand what's happening first. So I'm going to go back to my web page, and I'm actually just going to open up. I'm using Firefox, which has a built-in JavaScript emulator. You don't have to. You can use Node, for example, if you wish. However, a browser is typically provided in most operating systems with a JavaScript emulator. You can always, there's also free JavaScript emulators online that are also just as good. So let's step through this code line by line. It would be nice if I had this code to show. Let me see if I can pull it up. That's the wrong file. Let's see. I'm going to open up Ranger. Let's go to our, nope, we're doing our web demo. Nope, a web challenge. And then let's go to the definition of read secret. So I'm just going to copy this into our terminal or emulator, just so it's a little bit easier to reference things. So let's see. At the top, we're defining for file pass is some like string, right? So for file pass is some empty string, and then we're reading each character. We're doing for car of file name, and then this repeat.3. Okay, that's quite a lot's going on here at the start. Let's try to figure out what's going on. I'm going to move this over just so it's a little bit easier. So what I like to do sometimes when I don't know what something does is I just like to try to run an example of it for myself. So we're doing for car of, actually, let's start with this dot repeat command, right? What is it? What does it do? I'm going to type in banana. Sure, why not? And then if we do dot repeat, oh, the terminal autofills it for us, and we repeat 3 and run it, we see that banana in quotation marks, so banana as a string, dot repeat 3 just spits out banana, 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 or banana repeated 3 times. Perfect. And that's also another string. So it just seems to take whatever we put in and repeat it 3 times without adding any spaces or doing anything else. Okay, so now we have this dot repeat. We have a string. What does for car of file name do? Because that's weird. Well, we can think back to for loops. It probably iterates through something, but what most people would consider iteration as like for int I equals 0, I less than some maximum I plus plus. What does this of value represent in our case? So let's just try an iterator. So for I of, we're passing through a string, so let's do the same. ABC, 1, 2, 3. And then instead of like doing anything fancy, with I, we can just read what the value of I is per iteration. So I'm just doing console.log, and we see that for I of ABC 1 to 3, at each iteration, I is just one of the characters. That is A, B, C, 1, 2, 3, individually on its own. Okay, perfect. So at any point, this character, this car, is just a letter within file name dot repeat 3. How's everyone so far? Cool, cool. I'm gonna check chat. I don't use Emacs. I should learn Emacs. But anyways, let's figure out what the second line does real quick. I'm just gonna copy it into my clipboard. But we're taking that character, right? We're taking that character that we just got from our string, and then we're gonna put it to lowercase, which kind of sounds like we're taking any uppercase character, let's say capital A, and putting it to a lowercase. That would make sense. We're doing this car code at 0, which sounds kind of funky. Let's see what car code at 0 with let's just use a lowercase a, just because we're pushing everything down to lowercase. So car code at 0, that spits out 97, and I'm just familiar with it. But 97 is the ASCII character code, or the American Standard Computational whatever code for the letter A. Cool. So at this point, we're getting whatever character code is that, like, whatever character code, and then subtracting by a very similar character code, but of A. And I'm just going to go do a little bit of math, which some people definitely don't like, but I do. So let's go to my iPad. If let's say to go to G, right? The letter G. This is equal to the letter A plus some offset, right? So what G is A, B, C, D, E, F, G, the 7th character of the alphabet. So therefore, I think it would be A plus 6, so 0, 6, 7, yeah. So this offset, if this is index 0, then to go to the letter G, which is at index 6, we can add by some offset. And doing some algebra for this, we can see that our example, like we can see the reason why this person has wrote their line of code this way. I should actually just write this right by the line of code so I can just write it. We can see why they wrote this code this way. It's to do whatever character that we're looking at, so in this case, G, subtracted by A, and then we get the offset. So it looks like whatever character code is, this would be just the index of a given letter, specifically the letter of char. Okay, so then going on to the next line, right here, we have some comparisons. So if character code is less than 0 or character code is greater than 26, well, then it looks like we know that there's 26 letters in the alphabet, right? So if it falls, it looks like if it falls out of the range of of an alphabetical character, then it will put in a little period here. Okay, and then afterwards, it will go to this continue line and just go back, start the loop all over. We jump from here, go back up, and we do it with the second character. And then last but not least, we are doing some funky fresh string concatenation. We're doing like string dot from car code 3 times character code modulus 26. Lots of things are happening here, and it's a little crazy. So instead of trying to figure out what something like G would turn into by hand, because we're doing some like modulus stuff and we're doing some addition, let's just take our line of code, this one, and then I'm going to smack that right into our terminal. And instead of concatenating, I'm just going to read what this value is. So console.log, let's set let character car code be 6. Recall that 6 is G. So when we run that, we actually see that it seems to do some funky arithmetic to produce another letter. And then if we do that for another letter, let's say A is 0, then I have to use, I used let. We're good. Then it goes back to A, B would be 1, and it seems to just generate some weird set of values based off of each letter. And now we know we know effectively what each character is going, we know what this general loop does. And in fairness, we could just go through each line of each character within this file name that has been repeated 3 times and like do the modular arithmetic of everything. But let me let you in on a little secret. Recall that this entire code, this index.js, it's written in JavaScript. We have a JavaScript emulator. Let's just take that, put that there. And then I'm going to set this to a var because I don't want to get screwed over again. Let's just set the file name to what we want it to be. That's flag.txt. Go down to the bottom here and then read whatever the password is. That will be console.log file pass. Cool. And this gives us some weird string. But recall, that's kind of what we want, right? Because just before this, we were getting weird strings by passing in each letter. So let's try copying this, slapping that into our into the file vault as the password, clicking on flag.txt, and boom, bada bing, bada boom, we have our flag. Cool. So for the I'm going to go back to our slides. But really quick, are there any questions, Mariana? The C text just the pineapple. Yeah, I like pineapple on pizza. Let me give me a second. How's my screen sharing? Okay, everything's still back up. Perfect. So just to do a quick recap, we went over the file paths and just ended up kind of copying the code, like specifically the for loop, and then generating the password. But we also stepped through it and tried to understand what is actually going on. And this is after going through the code and isolating things. Okay, assembly time. Yeah, let's go, let's go, let's go. Oh, I apologize really quick to Cosmic. I was not paying attention to chat, but yeah, you were following along. I really, really appreciate that. I just have to jump between a bunch of monitors. It's just the vibe. Yeah, thank you so much. Okay, assembly time. Let's go. But first, what is assembly, right? We're here, this is an intro course. What on earth is assembly? Well, you might have heard that assembly is the most painful programming language. And you're not wrong. However, there's actually a reason for everything. So at the very top, I kind of showed the compilation process, or the process of taking your source code, the thing that you write on a usually daily basis. I'm guessing you're all computer science students. And kind of piping that through and spitting out something that you can run on your computer. At the very top, we have our source code. This source code is what you write. I'm going to stick to C, C++. I also threw in Rust in there because love Rust. And then that goes into our compiler. That compiler looks at our code, tries to figure out what we're trying to do, and creates an equivalent assembly. Okay, so we know how assembly comes out. And then after that, assembly is passed through something called the assembler. And then that's going to be translated from text, something that we can read, into machine code, something that the computer itself can read. So on the right side, I have three representatives of each box. At the very top, we have some C code that just prints hello world. At the second part, we have some assembly, which is, it has some human readable text. It looks a little weird, like it has LEA, RCX. It's a little confusing if you never looked at it before, and it's, trust me, I hope to give you at least some familiarity of it. I'll tell you right now that there's references for all of these sorts of things, and the references are great, including the 400-page instruction manual for assembly. I highly recommend it. I use it sometimes if I want to die. And then at the very bottom, we have some funky fresh characters, which are actually hexadecimal, but this hexadecimal is representative of the assembly just above it. So we're going so if we look at this slide, we can see that each line is a one-to-one comparison to a line of assembly that is just above it. So basically, this 4A to XD0C24, that's going to allow that computer to read, oh, we want to perform this instruction, LEA, RCX, RSP. Funky stuff. However, the fun thing is that we can take this code, take these numbers, and put them into any other computer, assuming you have the same architecture. That's a huge caveat. But assuming you have the same architecture, you can take this code, put in any other code. The machine can look at that and say, awesome, I'm going to perform LEA, RCX, RSP, whatever that does. And for those who are more detailed, we're looking at Intel x86 assembly today. Throughout your classes, you're probably going to learn ARM, which is for the computer science students in the room. And then if you're a software engineer like myself, you probably took or going to take Computer Engineering 369, which I really like, and you will learn MIPS 32 as dead of a language as it is. Anyways, let's look at some representative code for Hello World really quickly. Oh, I'm gonna have a drink of water first. Any questions so far? Any questions?
No questions.
Oh, thank you, Christina. Are you highlighting it or?
Yeah.
Okay. Yeah, it's okay. It's okay. Okay. Thank you, everyone. I really, really appreciate it. Okay, okay, I am sharing my iPad screen. Let's go to Hello World. So on the left, we have the source code. Recall that's the top of our start. That's something that we can really easily read. So we're doing some including. Anyways, if anyone has wrote something in C++ or C before, then you're probably familiar with what this code does. In fact, I would argue most programmers would probably be familiar with this type of code, and that is the hello world code, usually something that's you would write in order to make sure that you know what you're doing. Trust me, when I was first getting into C, God, it took me so long to figure out what on earth is even happening here. But anyways, on the right side, we can see some equivalent assembly that will execute this code. Oh, we have a question. Is learning x86 so important? Yeah, x86 is slowly getting out of phase. I would argue that learning x86 is still quite important, just because although x86 runs in 32 bits, which is a smaller amount of memory, and x64 runs in 64 bits, hence the name. Sorry, I got a little distracted there. I would still say that the fundamental concepts from x86 carry over to x64. So that's why I would always argue that being program agnostic is the best. You can learn like specific programming languages, whether that's high level or low level programming languages, and master one. But at the end of the day, you should be able to, I would argue that you should be able to at least take the basic concepts from one and move it into the other. I would like to preface that I made the mistake earlier that we're not looking at x86, we're actually looking at x64. That's the 64-bit equivalent. That's my mistake, I apologize. But yeah, being posted into chats really quickly, just because I just noticed it, are something called Godboat links. And these Godboat links are, in my opinion, really, really nice. Let me pull them up back on the slides. So that's going to be this Godboat link. If anyone wants to copy it down. What it is an interactive compiler that is done online. So what you're able to do is actually hover over each part of the assembly and see what the equivalent C code that was compiled to create that specific piece of assembly. And recall that each piece of assembly does a very specific thing. So therefore, it will usually carry over from one computer to another. It also supports a whole bunch of, different types of compilers and different types of assembly languages, but it's currently set up to represent the assembly language, the binaries that I sent to you earlier today. Okay, so let's get back into the assembly itself. We're doing some funky stuff right at the top. We're doing a push and then a move. I just know the names of these off the top, but you might, anyone who's coming into assembly for the first time. And yeah, no worries, Cosmic. I thought it might help. Anyways, anyone who's not familiar with assembly might get very overwhelmed at first. So I'll tell you right now that most things that start with an R, so that's like RBP here, RSP, RAX, RIP, all of this stuff, these are called registers. And what registers are, there's a very fancy computer engineering way of putting it. I'm just going to butcher all of it and just say that they're very low level variables that you can only change the value of. You can't add or reduce the number of variables that you have. And because of that limitation, assembly has to do a little bit of juggling. So pushing will push stuff onto something called the stack, which is where data is located, data is stored within random access memory. I'm not going to go into that too much. Move an LEA, or load effective address, will set values to your registers. So I keep on forgetting. I'm pretty sure it goes from destination on the left and then source on the right. Is that correct? Yeah, cool. I'm getting confirmation. I like that. So basically this line is equivalent to the to RBP is equal to RSP. If you're looking at if you're assuming these are variables. And then likewise, load effective address, you can consider these square brackets as like dereference if you're considering if you know what pointers are. Not everyone does, and pointers are a little bit of a pain, but this will dereference RIP, and this will put the address of RIP plus 0x E00 into RAX. Thank you, Cosmic, once again. This is reminding me that we're looking at Intel syntax for x64. There's two different types of x64 syntax, which I believe is due to historical reasons. That's namely AT&T, I think, and Intel. Most people know Intel. I like Intel. Let's just stick with Intel. So we have some like variable manipulation going on here: push, move, LEA, move. But the thing that might stand out to most people is this call function, or this call instruction. And this call instruction, it's basically just this. If you look at the binary as by itself, I guess technically if you look at the binary by itself, you see this and it means nothing. But we're calling the puts function. And if we look back over to our source code, that's what this code is doing. We're calling puts. So this call instruction basically executes one of the functions that we want to run. So when we hit this instruction in our CPU, it's going to say, oh, well, the developer who is making this code, they want to call this puts function. I am glossing over a little bit with the idea of setting up arguments and the sort. However, I'm not going to go into that today. So yeah, that's hello world. And that is hopefully a good explanation, at least a good start into everything. The next step is going to be looping. Looping involves something called jumps, or bouncing around in the code, as I like to think of it. So if we take a look at the source code once again, let's just solely focus on the source code first. We see that we have an array of numbers, specifically 5 numbers, going from 2, 5, 3, 6, and 7. So 2, 5, 3, 6, and 7. And then we have this variable called sum. Okay. And then we also have another variable called index. And then while, so we're doing a while loop here. So we're going to run the same lines of code multiple times. While index is less than 5, so because we're going from 0 to 5, we're probably doing this 5 times. While index is less than 5, our sum is equal to, I guess, adding the next value of our array. So if I draw this arrow really quick, this arrow points at index 0, which is what we initialized it to. It's going to add that value to the sum. And then at this index plus plus, it's going to move this arrow to the next element of the array, and so on and so forth until the end of the array, where once we hit this line, it's actually going to move past the array. And the index value here, this is index 5. Index equals 5. That's supposed to be an equals. I messed that up. Anyways, that's supposed to be index equals 5. And then because index is equal to 5, and the while loop is checking for strictly less than 5, then it's going to jump out and go over to our printf statement, which is going to say the calculated sum. If you're wondering, I do have, I'm not showing the slides, whoops. I do have these binaries hosted. If you want to ever interact with them, you can just use netcats, which is I think a networking tool. And they've also been put into the YouTube and Twitch chat if you are interested. They don't have any flags or anything. It's just in the case that if you want to interact with these. Anyways, moving on. We can now take a look at the equivalence assembly. And yeah, I'm not going to lie. I'm not going to fluff around. It's quite long. But recall that a lot of these instructions push, push, not that one, move, all these moves. Oh, wow, that's a lot of moves, right? Moves, that's still a lot of moves. All of them, those are just setting things up. And if you recall back to our web server, we don't have to take a look at everything to understand what's going on. So especially the inner workings just to get it working, right? So let's try to focus on some, I guess, more core pieces of code. So let's try to take a look for, well, last time we saw a call to our printf statement. So maybe we can try to look for that here. That's all the way down here. I'm going to highlight it. So, okay, we found that. And then moving up the code, we have this JLE instruction. Oh, okay, that's interesting. And then we also have this JMP instruction. And I'm going to tell you now that these two instructions basically allow us to hop around the code, like I alluded to earlier in today's workshop. So I'm going to take a quick look, jump over back to my Firefox. And I'm going to open up some references. Let's take a look at what is actually JMP and JLE. If I find my Firefox page again, ignore my to-do list, please. This is actually out of date because it's Monday, isn't it? Let's see. Need to go to my hack revenge. Okay, cool. So this website, which I can actually send in chat myself, this website has some really great documentation of to what are known as jump instructions, or jumps that instructions that tell you to jump around in the code and move to a different spot. So if we're looking for Cosmic pointed out JMP earlier, so we're going to look for JMP if I can find it. Sometimes it's not always here. It's not here. Well, I have another. Flip it down. I am actually blind. Oh, the letter M, like mango. Sorry. No, that's okay. My bad. I should have looked at that much earlier. I thought it would be there. I just have another. That's fudge. Where is it? Here it is. I have another web page for documentation like this. This one I actually prefer a lot more. We can go to JMP, which I know is here, and look at the documentation for JMP. And it's going to say some fancy things. Transfer program control to a different point in the instruction stream without recording return information. Wow, fancy, fancy. Basically, we're going to, once we hit this instruction, we're going to go to this address. So 125F, and 125F is, if I can find it, please, that's here. Okay, and then that's going to be our comparison. Wait, I'm gonna ahead of myself, and then the next part is going to be this JLE. We can take a look at what JLE does really quick. JLE. Now here comes my instruction set. JLE is jump if less than or equal. I believe this is strictly less than. So, okay. But if you take a look at the code itself, we're not actually making any comparisons. What does it mean by jump if strictly less than if we're just giving it an address? Well, if I erase the circle that I just created, we see the CMP instruction. CMP compare will compare two values, namely this variable, let's just call it a variable, this point in specifically stack memory with the value 4. Okay. But recall that JLE is going to jump if this value, gosh, my circles are getting a little out of hand, huh? If this value is less than or equal to 4, well, that has to then and because we're working in the field of integers, if you want to be a mathematician, because we're working with integers, index less than or equal or less than 5 is then equivalent to index less than or equal to 4, and that's what's happening here. So we can say that this point of code, this this JLE instruction, is equivalent to our while loop. How's everything so far? Cool, cool. I like thumbs up. Is anyone in chat complaining? No, not yet. Sounds good. And then afterwards, because we know that this will jump up to 124F, which is right 124F right here, moving along to here, then we can say that this code here, God, this is getting messy. I do have a laser pointer. This code here is going to be equivalent to this code here. And we can kind of see that, right? Because there's this add instruction. It says what it says, add. And then the second add instruction, again, does what it says, add. And we have two add instructions right here. So, and then if and only if that index is greater than 4 or is equal to 5, then we will not jump at this instruction, but go to this move instruction. And then that will go down. And recall that we pointed out our printf statement from earlier before returning. So that's the jump flow. I'm going to jump back to my computer, switch to a separate display again. And then I have to go back to my slides. Here we are. Okay. So, okay, punchy JavaScript is punchy. So again, we basically broke down our code and or the assembly that we were looking at into these parts that I've highlighted which I would argue are the essence of the program. And going even further, I removed all of the grayed out code to just focus on the code that we were just looking at. And we looked at the initial jump. It goes down to 125x, which then it does the comparison. The comparison checks if this D word PTR, whatever, is less than or equal to, or it makes a comparison, I should say. And then the very next instruction after that, JLE, that would make our comparison, or excuse me, God, I'm getting this mixed up. CMP makes our comparison. JLE jumps conditionally if our value is less than or equal to 4, as specified in the comparison line above. Yep, what's up?
You might have said this, but is that why the LE is there?
Is that why the
JLE?
Yes, JLE is equivalent to jump if less than or equal to. Again, I did send over a one of these ones. The Unix Wiz, I believe, has a good table, good reference to different types of jump instructions that I like to use. Okay, going back, and then assuming our value is less than or equal to 4, as we were checking in the comparison, it will go back up, do whatever was inside the while loop, and then jumps, does it again. It will do this 5 times until not jumping. It goes through the regular code call, and then go into our call instruction. How are we so far? Yeah, cool. So I just added some arrows here. This will just represent the overall instruction flow. So the yellow here represents an unconditional jump flow. It would just jump straight from address, yes, straight from instruction that's kind of prepended with 124D, which is the address, and it will jump down to 125F. So that jump instruction goes down to the comparison instruction. And yeah, Cosmic is on top of it once again. Cosmic is alluding to the idea that x86, excuse me, x64, I always say x86, will use another register called eflags. And this, you're actually setting the eflags register when you're calling CMP. So it would do every comparison you will ever probably need. And then JLE will then reference the eflags register before choosing to jump or not. So thank you, Cosmic. Last bit of assembly for today, I'm going to be talking about branching. Namely, this is your ifs, this is your else, this is your if-else in the world. And let's jump over to, oh, yep. Again, I have the Godbolt dynamic assembler for it. I feel like okay, no. Someone's helping me send links over, really appreciate it. Okay, so let's take a look at my iPad. Look at my iPad, please. Okay, so branching. Let's take once again, let's take a quick look at the source code. We have this array, 33 items. We're doing scanf. So scanf will read user input. And I'm putting this 32 value here. If you're not, this is to do with like fancy format strings stuff. This just prevents like, this ensures that only 32 characters are being read from input. So it asks, oh, what is your name? Puts that into output and then reads user input. And then if your name is longer than 16, so if the length of your name, str length, of your name is greater than 16, let's say you have 17 characters in your name, then the program says, wow, you have a long name. Otherwise, you have a short name. And then it just does that. That's all it does. Let's So if you thought the looping assembly was long, unfortunately, this one is just a bit longer. So, but we can already identify some of our code from before. So we have our puts. Let's see, that is somewhere here. Puts, puts. And then likewise, we have scanf. And then we have string length. And then we have another puts. We puts back puts. And then we now do another puts, which is interesting. And then it looks like we return just down here. Cool. Okay, but if you're familiar with like code, just the general idea of code, thanks Spring, we can usually things are executed from top to bottom, right? We did look at jumping, which allows us to jump from one code to next, but assuming you go through all of this, we have two puts calls right here, which is interesting. We have a call to puts and a call to puts, which because they're after our string length call, it has to be these two puts. It has to be those two puts command calls. So going through the code, assuming there's no jumping whatsoever, if we go straight through everything, the code will just say, oh, wow, you have a long name. And then immediately after, oh, wow, you have a short name. But that doesn't work, right? That's not representative. And of course, to solve this once again, we're going to be jumping. Please, iPad, allow me to write. We're going to be jumping. So once again, we see some more jump instructions. We have JBE here. We have a JNP here. Oh, gosh. I'm going to ignore this one for reasons. I have another one, I believe. I am blind. Am I blind? I swear there was another one. String length. Oh, nope. I think there's just the two. Okay. Anyways, let's, instead of going through this on my iPad, I decided to write this out on my slides because it's a lot nicer that way. So once again, I highlighted the individual instructions that we kind of pointed out, namely our function calls, puts, read. Read is just going to be the same as scanf. If you're curious, and to prove that, I'm going to move my kitty terminal over. And I'm just going to, oh, please. I'm going to do man kitty. Oh, not kitty. We want to do man read. I guess man to read more specifically, but let's do man to read. Man to read will allow us to read user inputs. Attempts to read n bytes of data from the objects, and we're passing in, just trust me on this, we're passing in standard input as our file descriptor. Okay, going back to the past. I've lost my cursor. There we are. So just know that read is equivalent to scanf. And then again, we have our two puts after the string length call. Cool. So I'm going to get rid of all the additional instructions that we weren't really taking a look at anyways. But I left in the comparison, which we now know is pretty important, but also and also the actual jump instructions. And now we can try to figure out what's going on here. So I apologize to those in chat. I'm going to be pointing in person. I can't point. I guess I can use a mouse cursor. I'll do this awkwardly. Okay, so we have JBE here at line 127B. We can take another quick look at what JBE does. I'm going to move this over. Come on. JBE, give it to me. Where are you? Jump if not. Well, nope, that's. I should have just mirrored my screen. Huh? Ah, here we go. Jump if below or equal. So I don't know why it shows JBE, but I'm fairly certain that that's just checking if the value is below or less than or equal to the comparison just before. Sorry, I'm just going to move my Firefox window back. Okay, so JBE just checks if this comparison, if RAX, the variable RAX, is less than 0x10. 0x10 is hexadecimal, and it's the value of 16, which we associate with. And recall that we're actually checking if the value is strictly greater than 16 for this for a long name. So if this comparison is true, and if this comparison happens, when the comparison happens, and JBE jumps, wherever it jumps to, it has to look for the shorter name. So it's jumping to 1296. 1296 is, no, excuse me, 1298. That's going to jump here, and it's going to execute all the way to LEA. Again, that's loading an effective address, and we're loading in the short string to be printed. So here we're reading the short string. If it doesn't jump, then we go through, we load in the long string, write it to standard output, and then we have an unconditional jump. This JMP instruction that is just going to go down all the way down past our puts call, which puts stuff into standard output, into 12b1, which is just past output, and it returns. So that's our conditional. That's our conditional statement. Either we go down the route of loading our long string and then executing puts, or we go down the route of loading in our short string and then executing puts. And there's some what are called disassemblers, like Radare, that do what I'm doing right here. And I'm just visually showing you a potential, like the conditional instruction flow that is occurring. So on the left is the red, and the red has no jump performed. So at the beginning with the JBE, so we're going to load in our long string, write it to standard output, and then call JMP, unconditional jump, and jump back all the way down to where we return. Otherwise, on the green side, we do jump. So therefore, the string is less than 16, less than or equal to 16. And then we call in a short string, call puts, but then there's no jump because the next instruction anyways is the set of instructions to get out of the function. Yeah, out of the main function. That works. Thanks, Brain. So any questions on that at all? I'll take silence as a no. Chat is always delayed, so I'll keep my eye on it. Once again, thank you, Cosmic. You are on it. I think there is just some delay. But really quickly, really quickly, I'm going to go through some tools. I created this assembly, like these assembly files to give you. I create, but there has to be a. So how did I do that? Right? I have the source file. I have the assembly. I'm not gonna write assembly by hand. No, thank you. So if you're taking computer science 355, you're gonna have to. Let's take a quick look at object dump, really quick. Object dump is, where's my kitty terminal? Is it on behind me? It is behind me. Excuse me. I'm gonna grab that, bring that back here. I'm gonna smack this into a mirror mode. Give me a second. Doopy doopy doo. Okay. So let's take a look at our branching demo. Yeah. The computer would stop dying. That would be nice. Okay. So object dump is a disassembler. So it allows us to take in a binary, something that we've already compiled that being said, we wrote that from our source all the way down to machine code. It allows us to parse effectively our binary, the machine code, and bring it back up to what's it called? To assembly. That's because that's what we were looking at. So this is the command call that I typically use to call an object dump. So object dump is, of course, the name of the program that we want to use itself. TACD just tells object dump, hey, we want to disassemble our binary. D, disassemble. M, capital M, then allows us to set our flavor of assembly. Recall that there's two types, AT&T and Intel. I'm just saying I want to read Intel because Intel is better, in my opinion. And then we're specifying what we want to disassemble. In this case, it's branch. So when I press enter, it's not good because I'm on Mac OS object. I have to, please tell me I didn't remove it. I Dockerized my CTF environment. If you're on Mac OS, I highly recommend doing the same. Okay, object dump, DM, Intel, branch. We read it, it kind of goes crazy, it kind of spits everything out, but it's spitting everything out into standard output. We can use a little bit of Linux piping to put that into less or into a file, which is probably the better thing to do. And we see a whole bunch of things. We see some scanf going on here. We see some puts going on here. So at this point, I would always recommend to go to user-defined functions, namely main, because every C program should have a main function. It's what you define to run your code. And this is exactly the code that I gave you. I'm not going to keep this up for long, but this is what I'm defining, or this is what I copied to give you the certain files. Yeah, so if you really wanted to, you can always call it object dump and then just do effectively what we've been doing for the past, I think, hour? Oh, God. Or if you want to stay sane, or if you're not studying at the core, you can do something called using something called Ghidra. Ghidra is known as a decompiler. So recall, compilation goes all the way down. Decompiling will allow us to go from our machine code, and it will spit back some C code for us. The C code is not always nice, just because it's trying to figure out what on earth is going on from literal numbers, but it gives us a representative of how things are happening, like what the original source code might be. So to run Ghidra, I created a Ghidra project in my directory. I don't know if you can always use the same Ghidra project. I always create a new one per binary. However, I don't know. It's just what I like to do. And then if you installed it using sudo apt install with Kali, you should be able to just run Ghidra just by itself. And then press enter, it should open it up. But for me, I'm on Mac OS. I had to go jump through some hoops. I have to run something called Ghidra run after. And there's instructions on this in the Discord announcement where we talked about installing Ghidra run, or Ghidra, excuse me. So running Ghidra run, fun way of saying it, will execute, will try to start up Ghidra. Just, sorry. We have a comment in the chat. I'm gonna just, Ghidra is written by NSA. Oh yeah, so Cosmic is correct. Ghidra is an open source tool developed by the American National Security Agency. And honestly, it's really nice that they will keep it open source. But in that same sense, if you don't necessarily trust the NSA for whatever reason, I suppose don't use it. There's alternatives like Cutter or Radaro 2. I won't be going over those at the current moment. So when we open up Ghidra, you would usually see a user's license agreement. Just do read it. I'm not going to tell you not to read it. I'm also not going to tell you to not read Apple's terms of service, but we know how that is. And then after that, we're going to go into this. Admittedly, right now it looks pretty messed up because my font size is way too big. But this this like project opener. So you can always create a new project. I always like to specify non-shared project. Go next. I give it a project directory, the directory that we just created, Ghidra prod, and then give it a project name. And then after doing so, you get this blank project. Perfect. Okay, so how do we actually decompile code? You can click on this little green dragon in the top left. Open up a window, and then you can go to File, and then Import File, or press I on your computer. It'll open up. Oh boy, I love scaling fonts. You can open up. It'll open up a file explorer, and then you can go to the directory containing all your binaries, or whichever binary you want to decompile. Let's do looping, and then let's decompile loop. It's going to try to parse it a little bit, give you some information about what the file is. You can just press OK. It will do its thing. Come on, Ghidra. And then it'll ask you, OK, you just imported this file. It has not been analyzed or has not been decompiled yet. So we would like to analyze it. It'll ask you, how would you like to analyze it? There's a whole bunch of options. I just choose to go for the default and just click analyze. You can also just press OK on this report summary. But afterwards, you can go straight in. Oh, I have a warning. This is because I'm running it through macOS, and there's some protected shenanigans with macOS. I'm just choosing to ignore it. Probably not the best. Anyways, on the left side, we see some. Oh, it's cut off. This is assembly. Wow, this is really cut off. On the left side is the disassembly, which is what we saw earlier. We have our LEA and move instructions, all that fun stuff. On the right side, we have no function. So we can go to, again, we should look for the main function. But to do that, I like to go through start_C and then go to this main value. This just helps in this case that if there was something weird about the binary you're disassembling, and the main function is not I guess it's defined, but it's not called main for some reason, you can go through start_C, which is placed there by the compiler, and it has to be there for a binary to run. Go to main, and then that's where you can start. Now you have your decompiled code. Wow, I actually wish I can zoom out in this case. Oh well. So, did I do loop? I meant to do branching. Whoops. Anyways, so once again, now we have a whole bunch of funky, fantastic things, right? We have some variable declarations like you would see in C, and then some array, putting into the array. Going back to the looping source code, we know that this local _28 is our nums array because we're putting in the values 2, 5, 3, 6, and 7. Afterwards, we're defining another local variable, locals30, to be 0. This referencing our source code. This is our sum, or the total number, total sum, thanks brain, between 2, 5, 3, 6, and 7. And then in here, we have a for loop instead of a while loop, but that's okay. It does the exact same thing because we're doing less than 5, and then we're incrementing here. And then this local underscore 2c, this will be our index. I would like to preface that I have been renaming variables, and this just helps with the reversing process. Oh, there's a question in the chat. If decompiling is efficient, why do we need to understand assembly to reverse engineer the program? A good question. A good question. Ultimately, I don't have a good answer for this, but in my opinion, from my experience, I should say, there are certain cases where Ghidra will skip steps or interpret things a little bit wonky. So it's a good idea to understand the assembly in order to, because that's going to be what is actually happening at the end of the day. For example, there was a case where I didn't realize that certain arguments were being loaded into a function call because Ghidra didn't place it. However, by looking at the assembly, I was able to see the instructions that set up a particular function call. Ghidra's pretty good at, or decompilers in general are pretty good at decompiling. That's their job. However, it's not always perfect. And at the end of the day, assembly is going to have the exact instructions, the exact things of what are going to be happening inside your binary. So I like to make reference to the assembly when I can. Okay, thank you for your question, Cosmic. I think it was Cosmic. But to go back to our decompilation, I was renaming variables, and I can do that by selecting, like putting my cursor over a variable that I want to rename, right-clicking, and then do rename variable, or as the symbol here represents, I can just press the L button, and I can rename it to what this variable actually is, or something that I know I can reference, which is index. Cool. I'm going to go back to my slides. There is one more challenge. We're almost running out of time, but I'm going to give you guys 10 minutes to run the last binary that we haven't looked at yet, and that is the sequence binary. It's hosted at 137.184.118.122. I don't know why I'm saying it. At port 43412. And then below are the object dump instructions, and then the key bindings for Ghidra. So I'm going to give you guys 10 minutes to work on that. Feel free to ask me any questions, talk. I'll be more than happy to discuss during that time. Yeah, what up, Ramirez?
Are we supposed to be able to run it?
No, you are not supposed to be able to run it. That's just because of some funky things that happen with the compilation process. There's some incorrect links is what it's called. Okay. I'm gonna also keep an eye out for chats in case anyone is mentioning anything. But beyond that, I have put 10 minutes on the board. So just take some good time. Sure. Wait, no, I'm gonna unmute myself. Okay. Yeah. So just really quick, anyone in chats, I just said that uh, there's a number. I'm just gonna open up the decompilation of it on Ghidra, just in case if anyone does not have Ghidra installed at the current moment. Um, just in the future, if you come to workshop, we do have a list of prereqs to install, but it is perfectly a-okay. I'm just gonna go through. Recall that you want to go to, oh gosh, when macOS yells at me, I'm gonna go to start C. I like start C, and then go to main, and then, whoops, that's 10 minutes. I'm gonna give another 5. Actually, I might as well just get into the solution at this point. I didn't realize that we were running out of time. Excuse me. I'm also going to decrease the size of Ghidra because, my goodness. Let's see. I'm going to make this 24. Sorry, give me a moment, everyone. Just get me right back. So I did give a hint to those who are in person, and that is to look for a mathematical equation. Try to going through what we did earlier today. Once again, trying to figure out what each part does, and then on top of that, looking for an equivalent equation. Just waiting for Ghidra to load. Meantime, I'm going to run. Okay, sorry. I don't know what happened. It looks like my computer is slowly running out of memory, which is always fun. They're not sneaky points, no. Just be patient. Okay, sorry for everyone who's online. I just got booted out. Hopefully this is easier to read. Let's go into the challenge binary sequence. It was already open. Cool. So I would like to go to functions and then start C and then go to main from there. So once again, we have a number of things. If you run the code, we see that the server asks us, oh, you want our secret flag, huh? Give us numbers to our secret sequence, and then they say that the sequence starts at 6. Okay, so let's see. We see the equivalence line. Oh, and then afterwards it says, it asks us for the next value and then waits in for user inputs. And then if we get that wrong, then it's just dies. Huh, okay. I thought there was another, yep, I forgot to flush it. Anyways, so we can go through this code. This is still a little too big fonts-wise, but I want to make sure that people can see it online. How about that? Yeah, that looks a little bit better. So we can see that here's our printf statement. Oh, that's not the right printf statement. That's what we're looking for. And to get to there, we have to make sure that this local 34 value is greater than 4, which I initialized here. And then if maybe let's double check. Yeah, so this is increasing by 1, so this is our index. So every iteration we add something to an array of numbers. If I can type. We add something to an array of numbers, the first number is set for us, so this is first num technically, which is just a random number, which then modulus by 10, and then it's going to read a value using scanf. This is what I mean when sometimes Ghidra doesn't properly decompile something. Like in this case, it looks like the scanf is not doing anything. But I'll tell you now, if you look at the assembly and understand something called the call stack, it's doing the correct syntax as you were to see with a scanf function call. So we call scanf. If index is 0, then it should be 1. So let's go back up here. Or no, it will return. Nope, that's BA. I can't read. It'll go back to our start. And then if the numbers is from our numbers, if index plus -1 or index -1, right? If the last number of our sequence multiplied by 2 plus 5 is not equal to our current value, which was written into the our numbers array. That's done at the scanf line here. If the last number times 2 plus 5 is not that number, then we see that the number doesn't follow the sequence. I'm surprised. There's a reason why it's not showing up, and that's my fault. But it will jump back to this lab 00101 3F7, and then it will close. This is actually our return value in that case, because we're returning, or I guess I should just call it ret. This is what is being returned. However, if it is that value, then we increment to next index and do this all again. So therefore, our sequence is, I want to type this down. Our sequence is C subscript n. I'm doing this in a very mathematical style. So actually, I have an iPad. What am I doing? Type. Let me go over to my iPad here. C of n is equal to C of n minus 1 multiplied by, it was 2, I believe, 2 plus 5. Just going to make reference to the Ghidra code again. As Cn, the last number multiplied by 2 plus 5 has to be our current value. Perfect. Okay. So we're getting a sequence start at 6. Okay. So the next value then has to be 6 multiplied by 2, 12, plus 5, which is 17. And thank goodness I'm doing my math correctly, because now we're going on to the next index. Otherwise, the program would crash. So 17 multiplied by 2, 36 plus 5, 44. Yeah, 34 plus 5. That makes more sense. 34 plus 5. Yeah. Cool. And then we have to do that again. Why did I set it up this way? 39 times 2, that's 78. 83, yeah. And then one more time. Let's do it. Okay, 83. That's going to be 166. Yeah. And that is our flag. Don't you love some like 8 p.m. math? Oh my God. Anyways, let's switch over back to our slide quick, just for our close message. Please don't crash on my computer. Please don't crash on my computer. Okay, so just to go over what we talked about today, effectively, we're applying this black box ideology. We're saying that a program, an application, a server will take in some sort of inputs, do something with it, and then spit it out. And we can identify, and we can keep digging into the application to figure out what's actually going on and how can we make this program do what we actually want. And to do that, we can pinpoint specific functions or I guess internal blocks that will allow us to achieve what we actually want. And it's at this point where I argue that reverse engineering is a really good fundamental skill to have for reverse engineering in general, like reverse engineering challenges, I suppose, but also for regular CTF challenges and even day to day, like if you're just going into development, it's really nice to have the ability to dig deeper and try to understand either what you're making or what someone else is making. But firstly, today we were looking at some reverse engineering where the source code was given or the binary was given. There are cases where you have to do things blind. That's where you do make like educated guesses, and this might be in the case where you're performing an SQL injection or an XSS or literally anything else that I can't think of off the top of my head right now. And beyond that, you can reverse engineer more than just regular computer programs. Today, we've just looked at binaries. However, you can reverse APKs. That's what Joel Reedon did if you attended our talk a couple weeks ago. Computer hardware, if you want to break open like a CPU, networks, like an entire network structure, you can reverse engineer those. Bug bounties are going to be, they basically allow you to do this and get paid effectively. So companies like Google, they know that there's probably issues with their code. So they allow people to try to figure out an attack to try to break things. And if you do find something, they'll pay you to not tell anyone else but them. So basically. And then I cannot stress the importance of man pages. Man pages or documentation or general research is super nice, genuinely super nice to figure out what is actually going on. Maybe you don't know what like some funky, fresh assembly instruction is. Just Google it, genuinely. Google is your best friend here. You need to figure out what's going on. So you can try to execute it for yourself, but Googling it, researching it, slapping it into DuckDuckGo, whatever, that's going to be your best bet. Here are some references, yada, yada, yada. I meant to do these in APA. Have some resources. I highly recommend. I got really lucky. Ben Eden just released a really cool video on reverse engineering TV censoring device. I highly recommend it. It's such a very good video. I also highly recommend Live Overflow's introduction into reverse engineering in 2022. It basically goes through the tools that we went through today and also some more. And it's also Live Overflow, so we will explain everything significantly better than I have today. So thank you very much. I really, really appreciate for all your time today. And if you're a mess, you will look for the line at the very bottom. There is one last flag. I'm not going to show how to do it. I'm not going to show how to get it. It's within our first demo web server. So have fun. I tried to get that flag. I meant to actually send in the Docker file for this, just so it's a little bit easier. Let's just say that the flag is at /flag, /flag.txt. That's the location of the flag within the demo web server. So that's all from me. I really, again, really appreciate for everyone who sticked it out the more than 2 hours that this lesson turned out to be. I am terribly sorry for going over time, but I hope everyone has a good night. Thank you very much. And thank you to chat. Very appreciated. Yeah, ending the broadcast now.